Scene script. Have you ever wondered if it's possible to walk through walls? In the quantum world, this idea isn't as far-fetched as it sounds. Welcome to the fascinating realm of quantum mechanics, where the laws of physics as we know them take a back seat, and the unexpected becomes the norm. One such marvel of the quantum realm is quantum tunneling, a phenomenon that challenges our conventional understanding of reality. So what exactly is quantum tunneling? Picture this. You're playing catch in your backyard. You throw a ball towards a wall expecting it to bounce back. That's what happens, right? The ball hits the wall, it can't get through, so it comes back. But now imagine if that ball, instead of bouncing back, suddenly appeared on the other side of the wall. Sounds impossible, doesn't it? In our everyday world, yes it is. But in the quantum world, this isn't just possible, it's routine. Quantum tunneling is a phenomenon where particles like electrons or protons can pass through barriers, even when they lack the energy to do so classically. This means that a quantum particle can end up on the other side of a barrier, even if it doesn't have enough energy to physically cross over that barrier. It's like the ball in our analogy magically appearing on the other side of the wall. This isn't a mere theoretical concept. Quantum tunneling has been observed and verified in numerous experiments. It's a fundamental aspect of quantum mechanics, and it has profound implications for our understanding of the universe. This bizarre phenomenon plays a crucial role in various fields, from particle physics to cosmology, and even in the workings of our everyday electronic devices. So the next time you throw a ball against a wall, remember that in an alternate quantum reality, that ball might just find its way through the wall. This is the magic of quantum tunneling, a phenomenon that defies our everyday understanding of the world. So, how does quantum tunneling work? Well, to understand quantum tunneling, we first need to grasp the wave-particle duality of quantum particles. Quantum particles, like electrons and photons, exhibit the properties of both particles and waves. So while they might seem to be localized in one place as particles, their wave characteristics suggest they can be spread out over space. Now let's imagine a quantum particle approaching a potential barrier. This could be an energy barrier, much like a hill. In the classical world, if a ball doesn't have enough energy to climb the hill, it won't reach the other side, but in the quantum world, things are a bit different. Here's where the Schrödinger equation comes into play. This fundamental equation of quantum mechanics predicts that there's a non-zero probability of the quantum particle being found on the other side of the barrier, even if it doesn't have enough energy to surmount it. This is like saying there's a chance that the ball will somehow appear on the other side of the hill without ever climbing it. Sounds impossible, right? But in the quantum realm, it's not only possible, it's a well-documented and experimentally confirmed phenomenon. We can think of it as a game of chance. Let's say we have a deck of cards. Classically, if we know a card is not at the top, we would say it's impossible for it to be drawn first. But quantumly, there's a small chance that it could happen. This is quantum tunneling in a nutshell. It's a process where quantum particles use their wave-like properties to bypass potential barriers and end up in places where classical physics says they shouldn't be. It's as if they're playing a cosmic game of hide-and-seek, popping up where you least expect them. Quantum tunneling, therefore, gives particles a chance to be where they shouldn't be. It's just one of the many ways that quantum physics challenges our everyday understanding of the universe. So, where does quantum tunneling come into play in the world of particle physics? Let's start with the concept of radioactive decay. This is where an unstable atomic nucleus loses energy by emitting radiation, resulting in the breakdown of the nucleus. But how does this happen? The answer lies in quantum tunneling. You see, within the nucleus, certain particles find themselves confined by a potential energy barrier. In classical physics, these particles would need enough energy to overcome this barrier, but in the quantum world, things work differently. Quantum tunneling allows these particles to essentially tunnel through the barrier, even if they lack the necessary energy to do so. This process leads to the emission of radiation, resulting in the decay of the nucleus. This process is not just confined to radioactive decay, it also plays a pivotal role in the very heart of the stars where nuclear fusion takes place. In these stellar furnaces, light elements like hydrogen and helium are fused together to form heavier elements, releasing tremendous amounts of energy in the process. But for this fusion to occur, the atomic nuclei must overcome the strong electrostatic repulsion between them. a barrier that would be insurmountable under normal conditions. However, thanks to quantum tunneling, these nuclei can overcome this barrier and come close enough to allow the strong nuclear force to bind them together. This is how stars, including our sun, produce their energy. If it weren't for quantum tunneling, the stars wouldn't shine, and life as we know it wouldn't exist. Quantum tunneling in particle physics provides a fascinating glimpse into the strange and counterintuitive world of quantum mechanics. It's a world where particles can be in two places at once, where they can spin in two directions at the same time, and where they can tunnel through barriers that should be impenetrable. Without quantum tunneling, the universe as we know it would look a lot different. Quantum tunneling doesn't just have implications at the smallest scales, but also at the grandest scales of the universe. To delve into this fascinating realm, we need to explore the theory of quantum tunneling in the context of cosmology. Quantum tunneling, as we've already discussed, is a quantum mechanical phenomenon where particles penetrate barriers that they shouldn't technically be able to. Now imagine this concept, but on a cosmic scale, where the barriers are energy states and the particles are entire universes. Let's consider the Big Bang theory, the prevailing cosmological model explaining the existence of the observable universe. The theory suggests that the universe began from a singularity, a point of infinite density and temperature. But how did this singularity come into existence? And what triggered the Big Bang? Here's where quantum tunneling comes into play. Scientists propose that the universe could have quantum tunneled from nothing, from a state of no universe to a state of universe. In the realm of quantum mechanics, even empty space isn't truly empty. It's filled with quantum fluctuations, temporary changes in energy that happen randomly. These fluctuations can give rise to particle-antiparticle pairs that exist momentarily and then annihilate each other. Now, if we scale this up, it's possible that a quantum fluctuation could have created a tiny bubble of space-time. This bubble could have then rapidly expanded in a process known as cosmic inflation, giving rise to the universe as we know it. This idea is still theoretical and has its critics, but it's a tantalizing possibility that could explain the origins of our universe. It suggests that our universe might be just one among many, each born from its own quantum fluctuation. Quantum tunneling, then, might be the key to understanding the birth of our universe. So, we've taken quite a journey through the quantum world today. We started with the intriguing concept of quantum tunneling, a phenomenon that defies our everyday understanding of how the world works. It's a process where particles like electrons or protons can pass through barriers that should, in theory, be insurmountable. In the classical world, this would be akin to walking through a wall. We moved on to the mechanics of quantum tunneling, diving deep into the world of wave functions and probability amplitudes. We learned how the wave nature of particles allows them to exist in a superposition of states, and how the uncertainty principle gives them the ability to tunnel through barriers. We also discussed how tunneling rates depend on the thickness and height of the barrier and the energy of the particle. Then we ventured into the realm of particle physics, where quantum tunneling plays a vital role. We discussed how quantum tunneling is responsible for radioactive decay and nuclear fusion in stars. We explored how it allows alpha particles to escape from the nucleus of an atom, leading to alpha decay. Our journey then took us to the far reaches of the universe, exploring the role of quantum tunneling in cosmology. We learned about its implications on the Big Bang theory and the fate of the universe. We also discussed its potential role in the formation of the universe and how it could lead to the creation of baby universes. In the end, what we've learned is that quantum tunneling, though counterintuitive, is an integral part of the quantum world. It's a concept that not only shapes our understanding of the microcosm of particles, but also influences the macrocosm of stars and universes. Next time you see a wall, remember, in the quantum world, it might not be as solid as it appears. Until next time, keep exploring the magic of the quantum world.